Today we're going to take a look at Gibbs free energy. Free energy doesn't really cost you anything. Oh, sorry, a bad joke. But free energy is a way of figuring out if a reaction will proceed on its own without outside energy, or if it needs energy to be added in. And if we figure this out, then we can figure out if a reaction is thermodynamically favorable or if it's spontaneous. Spontaneous doesn't mean that it occurs faster. It just means it occurs on its own without outside help. And you'll see spontaneous expressed in your book in chapter 16. But on the AP exam, spontaneous is actually meant by thermodynamically favorable, like we have over here on the bottom. So on the AP exam, it'll say thermodynamically favorable, and it means the process will occur on its own without outside energy being added in, like an ice cube melting at room temperature here in San Francisco. If we leave the ice cube on the table, what's going to happen over time? Well, spontaneously or on its own without outside help at this particular temperature, the ice cube will melt. And so that would be a thermodynamically favorable process. Let's take a look at how water and ice can coexist at 0 degrees Celsius. So we're going to use the equation. You'll see this also in your book at the bottom. Delta G equals delta H minus T delta S, where delta G stands for free energy. And then delta H stands for enthalpy change, like we've calculated before. T is the temperature in Kelvin, and delta S is the change in entropy. So let's go ahead and take a look what we have here. So I've laid out the units for you. Delta G in kilojoules, although you can have it in joules depending on which one you convert. In this one, I just happen to convert the delta S from joules to kilojoules, but you could also convert the kilojoules from delta H into joules and just make it match. So over here, I calculated the enthalpy change for changing from water solid to water liquid, and that is 6.01 kilojoules. And then the next thing we looked up is at 0 degrees Celsius is the temperature that this happens. So the phase change happens for changing from ice to water or liquid water, and that's 0 degrees Celsius. But we need to make that into Kelvin. So we need to add 273 like we did before with the gas laws. And then the last but not least, then I calculated delta S by using the products minus reactants. So the S of the liquid water minus the S of the H2O solid, and that was 22.0 joules per Kelvin. But then if you notice here, to make the delta H and make the delta S units match, we need to convert from one of them. So I chose to convert from joules to kilojoules by dividing by 1,000. You could multiply the delta H by 1,000 to convert it to joules just to make sure you have the correct units. So then I divided by 1,000, 22.0 becomes 0.022 kilojoules per Kelvin. And then now we're just going to cancel out the Kelvin. And then if we notice, then we end up with 6.01 minus, and then this is 6.01. Now, if you notice, the delta G is equal to 0. So when delta G is equal to 0, that means that the system is actually at equilibrium, which is a special case. So if delta G equals 0, then the system is at equilibrium. Now, if delta G is negative, that means that the reaction is spontaneous or thermodynamically favorable. So that means it would occur on its own. So what would happen if we actually increased this temperature here? Well, if this temperature went up, what would happen to the value of T delta S? Well, the value of T delta S would be greater. It would increase. And so as T delta S increases, that means that the number is going to increase greater than 6.01 for this part, the T delta S. So 6.01 minus a larger number will get us a negative number. And if we have a negative number, then that means that the reaction would be thermodynamically favorable or spontaneous. So that would happen if we increase the temperature, and it should make sense. Greater than 0 degrees Celsius, what's going to happen to ice when we leave it on the table? Well, it's quote unquote warm enough or at a high enough temperature where the ice cube will start to melt. So let's go ahead and take a look at the other way. Well, what if we decrease the temperature? So instead of 273 Kelvin, we use a smaller number, smaller temperature. Well, if the temperature decreases, that means that T delta S will become a smaller number. And then that means that instead of 6.01 minus 6.01, it'll be 6.01 minus a smaller number. And then that would get us a positive delta G. And a positive delta G would tell us that the reaction is actually thermodynamically unfavorable or non-spontaneous, which means the reaction will not happen on its own. You need outside energy in order to be able to for the process to occur. So what I mean that is anything lower than 0 degrees Celsius, the ice cube would actually stay an ice cube and it wouldn't change into water. But we could add outside energy, like we could have a torch, and we can apply a torch to that ice cube at that colder temperature in order to make that ice cube melt. So we could make a thermodynamically unfavorable process happen by adding outside energy in. So just to recap, if delta G is positive, the reaction is thermodynamically unfavorable or non-spontaneous. It will not occur on its own at that particular temperature. If delta G is equal to 0, the system is at equilibrium, and so it'll stay that way. And then if delta G is negative, the reaction is thermodynamically favorable or spontaneous, which means it will occur on its own at that particular temperature. And just to recap, remember, if it's spontaneous, doesn't mean that it happens quickly. It could, but it just means that the reaction will occur on its own without outside energy. It could be a slow reaction, but still occur. So hopefully that helps you out with delta G. And then don't forget this equation, delta G equals delta H minus T delta S.